take out the paper for problem-solving techniques, and you should have that piece of paper in front of you right now. We're going to talk about some of these AP testing strategies as we get closer and closer to the AP test. So we're going to take some notes today over some of these problem-solving techniques that you can use, and we're going to go through the sheet that you have in front of you. So if you have something else in front of you or a phone in front of you, let's go ahead and put those things away. Okay, you have a paper. If you'll turn that paper to the side that has the table on it, because there are two sides to that sheet. So the side that looks kind of like what you see up on my screen if you look behind that timer. I would like you to take 5 minutes to independently fill in as much of that table as possible. And then we're going to share as groups, and then we'll have a discussion. So again, take a moment to try to fill in what you can by yourself. I'm starting a 5-minute timer, and then we will revisit this, and you'll start discussing after this timer goes off. So, I'm going to ask you to now compare your what you've written down on your paper, your notes, with those the people that you're sitting with. If they have something you don't, add it to your paper if it's correct, or if you find out something you wrote down maybe isn't where you should have put it, you can take stuff off. But go ahead and revise your papers by talking with your group. So have those discussions, add what you can, and see if you can come up with a better idea of what you should have in each of these different sections. I'm going to start another 5-minute timer and give you time to discuss.
Okay, first thing is your kinematics is only like
All right. So hopefully you guys were able to fill in some more information to your tables. I'm going to go over kind of these different sections on the table, because what we're doing is I'm trying to make you think about how you would analyze a question whenever you read it, what unit you need to kind of recall and bring to mind, what equations you maybe need to be looking for on that formula sheet so that you can address these different questions that you might see on your AP exam in next month. Or on the practice one this weekend, or on the one we're going to do in class as an RA next week, starting on a week from today, actually, on the 19th. So let's go ahead and take a look. So if you have kinematics, and what I did was I filled this in with the answers that my students gave me last year. So I'm going to kind of fill in mine, but if you guys have something else, make sure that you call it out, and I'll ask at the end of each section. Maybe we can add even more in here than what I already have. So kinematics, first thing you write down. Actually, I'm going to ask y'all, what is the first thing that you said that you would write down? Bobby. Yeah, that table thingy so that you can label the variables. Label your variables. Given, same thing. Positive direction, that's a great answer. Okay, I think that might be the first one I have up here. I can't remember. Yeah, define the positive direction. Okay, guys, you have to make sure that you define the direction so that if you do have information there, if it is a kinematics problem, maybe your velocity is in one direction and your acceleration's in the other, you're going to need to know that for your calculations. So you need to start by identifying that positive direction so that you can appropriately label those givens, okay, which is the next thing. So you guys have the same answers they gave me last year. Find the appropriate equations. That would be a good next step, okay? And we're kind of just walking through steps. These aren't all the first thing you would do. Obviously, they're just things that you would do before you can solve the problem. Okay, but find the appropriate equations on that formula sheet. So if you take a look and you've okay, I've labeled these things, what can I do with it? Okay, so take a look at that formula chart. Your kinematic equations are the first 3 of them, equations on that sheet toward the left, top left of the page. Okay, here's that table, especially if you're trying to separate the X and Y directions. You guys picked up my mind maps sheets yesterday, and I had somebody ask me what the difference between one-dimensional and two-dimensional motion was, and it's this right here. If you have your object that's just going in the X direction only, and all of that motion and acceleration and everything's happening in that direction, then you are only in one dimension. But as soon as you introduce something happening in another direction, x and y, well, now you are dealing with two-dimensional motion, which would be like our projectile motion or circular motion, things like that. Okay, but you can obviously address those things with kinematics as well. So if you do have things happening in x and y directions, then obviously you'll need to label both. Maybe you need to graph things, or maybe you're trying to interpret a graph. So you need to think back to the different types of representations of motion, because if you're looking at a question and trying to figure out what you have to work with, perhaps interpreting those graphs or maybe even sketching one might come in handy. I don't know. But we've talked about position time graphs. Those are xt graphs. Velocity time, that's vt. At is acceleration time. And we also use those dot diagrams at the very beginning of the year to show when we had constant motion or accelerated motion. Again, you can add any of this to your page. All right, so that's what I had for kinematics. Does anybody have anything else that they would like to add that you got on your paper from discussions at your table that you want to share with the rest of the class? No? That's okay. We can talk about the next topic was forces. And some of the things that we wrote on under kinematics would still be appropriate for forces. But this is the first thing we said last year, free body diagram. Okay, if you have a question dealing with forces, sketch those forces. Draw that free body diagram. Okay, now we have two different types of free body diagrams that we've used throughout the year. We have rigid body diagrams, which we used in the rotation unit, where the forces have to be drawn at the point of contact. And we also have no internal structure diagrams, where everything is drawn at the center of mass. Okay, so you need to figure out what type of free body diagram. Are you dealing with a point mass, or are you looking at something where it matters that your force is applied 2 meters away from your axis of rotation because you're dealing with something that would rotate? Okay, and so you need to make sure that you draw those. Again, if it is rigid body at the point of contact, like on the last test, some of you lost points because you did not draw your force of friction and your normal force at the point of contact between the hoop and the ramp. Okay, and then some of you drew FG from somewhere else, although most of you got that one from the center of mass, so that was good, which is always where you draw FG. Okay, but again, free body diagrams, always a good place to start. Identify your system so you know what forces to draw. Okay, is that an internal force to the system, or do we need to draw it because it's an external force acting on your system? Because we're not going to be drawing those forces that are internal to our system. We're only looking at things that would cause acceleration of the system, which means we're only looking at external forces. So you do need to be careful with the way that you have defined that system, so you know what forces that you should be drawing on that diagram. Okay, once you've kind of started there, a good next step would be second law equations. Okay, do you have a net force in the x direction? Do you have a net force in the y direction? Okay, you can write second law equations to give yourself a way to start looking at how the forces that are there could cause acceleration of that system, or whether there is acceleration of that system. So again, write those for both the x and y direction. Of course, if you don't have any forces in one of those directions, let's say everything is happening vertically, then you would not need to worry about necessarily writing anything for the x direction. But if you do have forces in both x and y, then you definitely want to write out those equations. Define the positive direction. Again, you should still be doing this, and I probably should have put it up at the top. Okay, because when you draw that free body diagram, or whenever you go to use it to write the second law equations, you do need to make sure that you know which way is positive so that you can add your forces appropriately, because technically when you're finding that net force, it is the sum of your forces, but if one of them is to the left and one of them is to the right, you need to account for that in that calculation that you're doing. So define the positive direction. Okay, and then lastly, I had third law force pairs. And I mentioned this because you guys had a question on the test that you have been working through your corrections on, where there was a ladybug walking on a disc. Okay, and it told you what direction the ladybug was walking, but you were more concerned about how the ladybug affected the disc. And some of you forgot about Newton's third law. Okay, if the ladybug is walking counterclockwise, then that means the ladybug's force on the disc would be clockwise. Okay, so you have to think about that force pair. And so, again, sometimes you'll be told about one force, but you'll need to use the other part of that force pair for your calculation. That's exactly what happened in that question with the ladybug on that disc. Does anybody have anything else to add underneath the dynamics section for the first thing that you would write down? No? Okay. All right, kinematics indicators that it might be this type of problem. So how do I know it's a kinematics problem? Well, if I'm looking at it and I see constant acceleration math, it's a good chance I can use kinematics to solve it. Doesn't mean it's the way you have to go, but you can if you have constant acceleration. Of course, you cannot use kinematics if you do not have constant acceleration. Okay, projectiles. If you see a question involving a projectile, you're probably going to need to use kinematics in order to answer that question. Whether those projectiles are launched or dropped just straight down, again, same thing. Okay, and then you might have an XT graph. Okay, if you're given an XT graph, then you could use that graph to determine the velocity by finding the slope of your position time graph, which you could then use in some kind of kinematics question. So if you are given a position time graph, or maybe even a velocity time graph, you can use the slope of those graphs for some information. The slope of your velocity time graph, again, as a reminder, is acceleration. Okay, so if you have some position graphs, then those might come in handy. By the way, the area of that velocity time graph could also be something that you were asked to use, and the area of a VT graph is displacement. Okay, so that would be another thing you could get from a graph. So if you are given a graph and you have something, you might need to analyze that and figure out if it is a kinematics problem. That could be a sign, if you have an XT or VT graph, that you could approach that question with kinematics, so long as your graph shows constant acceleration. Okay, if you have an AT graph, since your acceleration would be constant, so that wouldn't be super useful because it would just give you the acceleration. However, the area of that graph also has meaning. The area of your AT graph would represent the change in velocity, okay, of that system or object. Does anybody have anything else to add for any indicators that you might be dealing with a kinematics problem? I thought of another one right now that we could add to this. If you had like a dot diagram, since we already mentioned that, so if you see those dots, that might be another indicator that you're dealing with something that might involve kinematics. But if you'll have anything else, again, make sure you speak up, because you guys have discussions at your tables. Maybe you have something else on your paper, and it might help everybody else in the room. All right, dynamics. Indicators that it might be a dynamics question. Obviously, if you're given a free body diagram, it's a pretty safe bet that you're probably going to be using that free body diagram and analyzing it in terms of the forces, which is dynamics. So if you're told about forces in the question, or if you're told or given a free body diagram, that would be a good indicator that you need to use dynamics. Elevator questions or pulley questions. If you see something with an elevator or a pulley in it, again, same thing. We analyzed those previously during our dynamics unit, and it's likely that you would be asked to do the same if you saw something like that on your AP test. Newton's third law. Again, for example, if you had something that says, like, compare the force on the cannon with the cannonball that is fired. Okay, you need to remember that those are going to be equal and opposite. For every action, there's an equal and opposite reaction. Or like the ladybug thing that we mentioned a second ago. Okay, you might have to use just some piece of the dynamics unit in order to figure out that part of the question. If you have a ramp without rolling, okay, then you could use dynamics. If you do have rolling, of course, it's involved, but then you're going to have to also bring in the rotation unit that we talked about. VT graphs, again, you could absolutely use these. And if you see a VT graph, it could be something that indicates that you're going to have to solve a problem that involves dynamics. That's because the slope of that graph is acceleration, and of course we could use that with Newton's second law, F net equals ma, if we had an acceleration from a VT graph. And then last one that I had up here is torque. If you do see torque, obviously that's going to involve forces, but you would then have to be combining some amount of discussion of forces and dynamics unit with some of our rotation units. So again, a lot of these are going to have overlap where you use multiple units or information that you learned throughout multiple units in order to answer those questions. Oops. Does anybody have anything to add? Sorry, before I move on, anything to add underneath dynamics for indicators that it might be that type of problem? No? All right, then let's look at the other two parts of this table, which are two more of our units we did this year, energy and momentum and impulse. Okay, if you're dealing with something involving energy, the first thing that you would write down would be your system. Start there. Okay, that way you know what form or forms of energy to consider, because if the Earth is not in your system, for example, then you had better not be talking about gravitational potential energy. Okay, if you do not have a spring in your system, then you had better not be talking about elastic potential energy. So define your system so that you can define what energy forms are present there and which ones are going to be forces doing work on your system. The next thing you might want to write down, this I think a lot of you found it helpful, was energy bar chart, looking at the forms of energy that exist maybe before and after if you're looking at something like sliding down a ramp or falling or a pendulum at two different points in its swing, whatever it might be. Those bar charts would help you to identify what forms of energy were present at point 1, wherever that is, and then at point 2, wherever that is, so that you could better analyze that question. Obviously, conservation of energy. You could use that bar chart to write an equation using conservation of energy to show that the one formed is converted into another. Okay, work, again, depending on what your system is. Sometimes, like I said, you're not going to have, for example, gravitational potential energy, but instead, because your system is just the ball, you might have work being done on the ball by the Earth's gravitational field, and then you'd have to consider work. This was our equation for total mechanical energy. So as you're looking at the energy present in that system and whether it is conserved or not, remember that your total mechanical energy is equal to the sums of your kinetic energies and your potential energies. You have two different forms of kinetic energy, translational and rotational kinetic energy. You have two different forms of potential energy, gravitational and spring or elastic potential energy. So again, you could write out an equation to determine the total energy present in that system. And then power. Okay, kind of related to work because power is the rate at which that work is done. But that would be another indicator that you're dealing with something related to energy, or it could be something that you need to write down depending on what information you're given in the question. Anybody have anything to add for energy? No? All right, momentum and impulse. First thing you should write down when you're dealing with momentum and impulse. Again, your system. Okay, you need to define that system so you know whether you're dealing with a situation where you have conservation of momentum or maybe you don't, depending on how you define that system. Does your system include all of the colliding objects? Okay, if so, it's conserved. Maybe the equation. Okay, look at that formula chart. Momentum is mass times velocity, P equals m times v. Or maybe you're dealing with angular momentum. L equals I times omega. That's your angular momentum is equal to your moment of inertia times your rotational velocity. Collisions. Guys, that means you're going to be using conservation of momentum. But if you see a collision, you had better be analyzing that collision through the lens of momentum and conservation of momentum. Because remember, that kinetic energy, that energy is not always conserved, but that momentum is if you define your system to include all of those colliding objects. So it's a better place to start Okay, unless you can tell in the question by the wording that it's elastic, then you could start with energy, but otherwise start with momentum. Okay, and that conservation of momentum equation. As a reminder, with those collisions, you can also find out something about energy. Elastic collisions will conserve that kinetic energy, inelastic collisions will not. Perhaps an FT graph. Okay, maybe the first thing you write down is the area underneath that graph, because you know that that area represents the change in momentum or the impulse. That's the same thing. Okay, so maybe you have an FT graph and the first thing you're writing down is the area underneath that line on that graph so that you can get some information to use for some other step later on. Again, conservation of momentum I already mentioned with collisions. That is what you would do as you analyzed a collision. Does anybody have anything to add for momentum and impulse? Again, there could be other stuff. This is just, like I said, what we put in the chart last year with my class. Okay, if y'all don't have anything else, we'll just keep going forward. All right, indicators that it might be an energy problem. Okay, again, obviously if you see the word energy in the question, pretty obvious, then you know that you're dealing with something where you're going to be considering energy forms. If you see a change in elevation or height, you can obviously analyze that through energy. You could possibly also analyze it through free fall, depends. Okay, on what information you have, or dynamics. Again, depends on what information you have. We're just looking at possible ways to analyze it. Is this possible? Yes, it would be. Okay, if you had something that had a change in elevation or height, energy would probably be the easiest place to start, depending on the information that you had. That could be a roller coaster, a pendulum, something going down a ramp. Okay, if you have rolling motion, energy is a good place to start there too, where you're dealing with the conversion of your, for example, gravitational potential energy in a ball earth system where you have a ball on top of a ramp, and that gravitational potential energy is converted into both rotational kinetic and translational kinetic. You could write an equation like that for some of those rolling motion types of problems. Again, work or power, if you see a question that involves the words work or power, or graphs that show those things, something like that, that would be an indicator that you would probably want to think of that, how to solve that through energy, a lens of energy. Anybody have anything to add for indicators that we're dealing with an energy problem? All right. Last one then is momentum and impulse. Indicators that it might be that type of problem. Obviously, if the question refers directly to finding momentum or impulse, that one's pretty obvious. Collisions, in all caps. Again, if you have a collision, please analyze it through momentum. Conservation of momentum specifically is a good place to start with those. Okay. Internal torque of angular momentum, again, as a reminder, does not cause a change in angular momentum for the system. That's something that they came up with last year. But again, indicators that you might have that type of problem. If you see a question about angular momentum, you do need to remember this, so that your any torques that are internal to the system are not going to cause a change in angular momentum, just like any forces that are internal to the system aren't going to cause acceleration of the system either. All right, that's all we filled in there last year. Does anybody have anything to add underneath momentum and impulse, that indicators that it might be that type of problem? I think I mentioned this on the other one, and maybe it would fit better here, but in the previous, for how to know that it's this type, or what to write down first. But if you have a force time graph, obviously we already listed that, but that would be an indicator that you're dealing with something involving momentum or impulse, because you would be able to find your change in momentum from that graph. I'm sure there are other things we can add, and you guys may have some of those things. Hopefully you do, but if so, you hopefully share them. So again, add to your table. If you want to add this in there, if you are asked to derive an equation, which you will be, one of your free response questions will be a derivation on the AP exam. It always is. Then 90% of the time, you should start in one of these ways. Again, it depends on the question, but derivations almost always start with either conservation of momentum, conservation of energy, or a second law equation. And sometimes you're using more than one of these during the derivation. Okay, but those are where you should start. So if you see something where you're deriving an equation, you need to think, can I solve this with momentum? If you're like, yes, cool, go. If you think, no, I don't have enough, then try energy or try a second law equation, but kind of go through in your mind, can I solve this with momentum? Can I solve this with energy? Can I solve this with Newton's second law with F equals ma? But you might want to add that to your table underneath the appropriate sections, that derivations usually start with one of these. All right, so I'm going to pass out a paper to you now that is a released FRQ question from a past AP exam. This is a class set, so you cannot keep it. It says class set at the top. In fact, I don't want you writing on it either. But what I would like you to do is I want you now to, having gone over all of these things together, I want you to analyze this question. If you flip your paper over, there's a checklist on the other side. You don't actually have to solve the question. In fact, I don't want you writing on it. But I want you to analyze what might we be able to use to solve this question. Now, if you want to go through and try to solve it, you can. But let me pass these out first, and then we're going to set a timer for 5 minutes so that you can complete that checklist. Again, do not write on it, but take a look at it. Now that you all have one, you are filling out the checklist. Check the boxes on the other side of your paper. And I'm going to set a timer up here. You have 5 minutes. We're just identifying what approach you might use. You do not actually have to solve this right now. So take a few minutes to talk to your group and fill out that checklist. All right, guys. I don't know why this thing is being weird. All right, so again, when you filled this out, identify the motion or motions occurring in the problem. Hopefully you realize that you were looking at linear and rotational motion, specifically vertical and rotational motion. What were you asked to find or determine? Angular velocity and rotational kinetic energy. Again, I'm not looking at the sheet. This is just filled in from last year. But if you read the question, those are the things you're looking at. So when you go in to check the boxes for the different content selection, what would be appropriate? Obviously, the kinematics stuff. You could absolutely approach it in that direction. Again, we aren't actually solving anything here, but if you even had different questions with the same scenario, okay, you could approach it by analyzing it through kinematics. Dynamics wouldn't be super helpful here, okay? Obviously, circular motion and gravitation would not be either. But energy definitely would, okay? Because we could analyze that linear and that rotational kinetic energy and the forms of energy that are present. Potentially, again, we don't know if that's what would be most useful, but we could analyze a situation like this. Okay, what about momentum?
Yes.
Yeah. Okay, specifically rotational. Okay, and then simple harmonic motion, no, not really. Okay, so again, just checking what you would look at so that you can start to focus on those specific equations maybe, but on those topics as you're trying to think, because you have a lot of stuff to kind of sort through in your mind as you're working through these problems. We've covered a lot of material this year. So being able to kind of hone in and focus just on the appropriate section is going to be important as you work through questions on the AP exam. Okay, identify the system. Again, this will depend on how you approach this problem. Okay, because we discussed several different ways to potentially approach it. So if you're looking at angular momentum, for example, then you would want to just focus on the diver. But if you're looking at this through a lens of energy, then maybe the diver-earth system. Okay, so again, it depends on what you're trying to do, what method you're using to get there, how you're solving it. You might have to define your system differently. Okay, all given quantities, there is nothing here in this particular question. There's no numbers. And then useful equations, again, depends on your method. We talked about different methods, so you would have a lot of different equations that are potentially useful. You could use the angular momentum equation or conservation of energy. Those would both be potentially useful equations to use. I didn't put kinematic stuff up here, but obviously you could go that route as well. Okay, since we checked those boxes too. But again, You can fill out the rest of that sheet there on your problem-solving techniques notes. And if you were wanting to actually work through it, okay, and solve the question, okay, I did find somebody who worked this thing out. I don't know that they were supposed to, but they did, so it's already out there, so I may as well tell you about it. On YouTube, on a channel called Math and Physics Tutor. And the title, if you are trying to search for it, if you want to check and see how you did, for those of you that tried it, or if maybe you just want to look it up later to look at an example, it's titled Rotation Free Response Paragraph Questions. I did include a link down there as well. Okay, so what I need from you right now is I do need the FRQ back from you. You can't take it out of the room, even though somebody put it online, but I do need it back from you before you leave today. So please bring those. You can collect them at your table, and somebody can bring it back up here. You are holding on to that note sheet. That is yours to keep.